Do you guys have any doubts regarding the question?
There was some assignment problem. There are some assignment problems regarding on uh, week 7
Which assignment?
and 8. Week 7 and 8
Assignment 7.
mostly.
Question number?
So, this
Question
is
number?
a mathematical question.
Which question? Uh, you can share your screen.
Hello, sir.
Hello?
Sir, can you, sir, if possible, sir,
Yes.
give some idea about theory part of MOSFET and the substrate bias effect and subthreshold conduction?
Sub-threshold conduction.
Yes, and the short channel effect. These are the, sir, MOSFET part. If MOSFET is a chapter, I think in week 8, sir. Whatever you can discuss in week 8, sir, your slide, if you explain one more time, it will be helpful, sir.
Okay, let me see if my slides are helpful, or I will get some other.
Yes, sir, no issue, sir. I just want to understand the concepts of MOSFET.
Okay. So this part you understood, right? How a MOSFET works.
I can understand, sir, MOS capacitance, how the your accumulation, inversion, depletion is formed. Up to that, I understand. But the difference between MOSFET and MOS capacitor is that the in case of MOSFET, the substrate above substrate part will be not present.
No, so MOSFET is basically MOS capacitor plus you have a drain and source.
Yes, sir. Drain and source. Yes.
So this is your MOS cap, and then you added a drain and source here. That makes it a MOSFET.
Okay.
So basically a MOS cap. It's a MOS capacitor. So it's a
Yes.
capacitor. So there's a dielectric in between, there are two conducting parts. One is metal and one is semiconductor, and there's a dielectric in between. That's how it acts as a capacitor.
Yes, sir.
And then you make it so. And what is a transistor? Transistor is basically a 3-channel device where you can modulate the current.
Yes,
That
sir.
that is a transistor. So you add a source and drain, and now you can modulate the current between the source and drain with the help of your MOS cap part. So that is how it's called a MOSFET, metal oxide semiconductor, and it's creating a field effect. So this the modulation of current is through a field effect. So that is why it's called field effect transistor. So
Okay, sir.
you give a field across your oxide by applying a voltage on a metal part, and your substrate is also, you have applied a voltage. It's called That's called your
Body.
body. Substrate is called a body. So body is generally grounded. It's kept at zero
Yes.
voltage. It's kept at ground, and you give a voltage to your metal part that creates an electric field across your oxide.
Yes, sir.
So, and that electric field creates your accumulation or inversion charges in this small region near your interface.
Okay.
That is why it's called field effect. And so since your body is p type, your drain and source are n type, so they are opposite type of carriers.
Yes, sir.
Hence there will not be any conduction from your drain side to your source side, or source side to drain side. But
Okay.
when you when you give, give a voltage to your metal and create inversion here, you create inversion charges on your substrate near the interface.
Okay.
So then this becomes an n-type channel, and now there's an n plus connected with an n-type channel, and now it's a conducting channel. Now it can conduct current from your drain to source.
Okay, sir.
So in accumulation, so when this is in accumulation, your transistor is off. It is not conducting. And when it's in inversion, your transistor is on. Now it is conducting charge.
Okay.
So that is why a MOSFET is typically used as a switch.
Okay, sir. Sir, I have asked you a question, sir.
Yes.
Whatever you told that, sir, in case of MOS cap, we found that the three regions: accumulation, depletion, and inversion.
Yes.
But in that case, sir, when we apply positive gate voltage, so the substrate will be P type. So hole will be repelled back, and it will create a depletion region.
Yes.
So sir, now if I apply positive drain voltage and ground source, positive drain voltage and ground the source,
Yes.
then sir, there will be a source to drain current will be flow.
Yes. If you have, so your here the source and drain are n plus. So you need a n type region to flow the current.
Yes, yes, sir.
Otherwise, it's just NPN, which is a
Now,
diode. Diode does not conduct current in like
yes, sir.
negative
Yes.
and reverse bias type, right?
So it will be act as a conductor, simple conductor. N plus and N region.
Yes.
Now, sir, my question is that uh, here in this MOSFET, how we can identify the accumulation region, depletion region, and inversion region? Because, sir, in case of metal and your oxide, and in case of metal, you have your dielectric and oxide, you can create some band bending is there.
Yeah,
In case
that
of,
is band bending is in this region.
yes, yes, sir. But sir, in case of MOSFET, how you can draw the graph, sir?
No, so the graph, see, so when you have a MOS cap, the graph that you draw,
With respect to work function, sir.
no, so this, so the graph that you draw is metal, oxide and semiconductor, right?
Yes,
So a graph that you draw is like this is energy versus x,
yes.
energy and x
Distance.
distance. So if let's say your band bending is like this, okay.
Okay, sir.
So if you see here, your this is your Fermi level EF.
Yes,
This
sir.
straight line is your Fermi level. So if I make a cross section here, then you can see this Fermi level is close to your conduction band.
Okay. Then it will be formed, sir,
This,
N type.
yeah, this will be your N type.
Yes.
And if you look here at the interface, your Fermi level is close to your valence band.
This is P type.
Yeah, so this is P type. So this is inversion or near inversion, weak inversion region.
Okay, sir. Okay.
So that is how your MOS works. So that if you draw, if I am that's like drawing a cross section here this way. If I draw cross section this way, then I will see this diagram, or
Yes,
maybe,
sir.
or this is P inversion in N type, or you can draw it like so. This is like your substrate is P type. This is your substrate region, and near the interface you have N type region. So this,
Sir,
yes,
sir, numerical parts of weak element, sir.
what?
Uh, the numerical parts of weak element, I need, sir. Weak element question number, weak element, sir. Hello.
Hello, wait. Uh, so which assignment?
Element, sir. Numerical parts only.
Question assignment 11.
Element, sir.
Can you type in chat? I am not able to understand.
Sir, I think he says that assignment 7, 7, 11 number question, sir.
Okay. This question. This question you are asking.
Yes, sir.
Okay. A MOS capacitor is doped with acceptor dopants of 10 per 16 per centimeter cube, assuming an intrinsic carrier concentration of 1.5 into 10 per 10. Find the value of depletion width on the onset of inversion. So at the onset of inversion, your this thing, what it's called? Uh, So you have to use from previous question. So so you calculate this. Did you calculate 10th question? You understand?
Sir, total numerical parts, if you kindly
Okay.
help to understand, then it will be
Sir,
helpful for
here
me.
2 pi f means this is strong inversion, na?
No. So 2 5f is yes. So at the onset of so your band bending cannot go beyond 2 5f.
Yes, yes.
So 2 5f is the maximum band bending. So when the band bending is 2 5f, we call it inversion. That is true that it's called strong inversion, but so actually there is no such thing as weak inversion and strong inversion.
Okay, sir.
We call it weak inversion and strong inversion because even in the weak inversion is your region in the depletion region.
Yes, sir.
The inversion that you call is strong inversion only. Weak inversion, the part in the depletion region before your threshold. So at the onset of inversion means your threshold. At threshold voltage, your band bending is 2 5f. That is called onset of inversion. Just before threshold is your weak inversion.
Okay, sir.
So this is the formula for depletion width at the. So the formula is this: to under root of 2 epsilon si psi s by qna, and at the onset of inversion of psi s is 2 psi 2 your psi s is 2 psi 2 5f or 2 5b, and your I am having trouble remembering the formulas. So from 10 per 16, you can calculate your EF. That is yeah, so if 5F would be your EC minus EF, right? So you use this formula 5F KT by Q ln Na by Ni. So you see it's the same formula. You see here, Sanjeev.
Yes, sir. Yes, sir.
So it's basically the same. Na is 1 into 10 per 16 you are given in the question. Your doping density you are given 10 per 16. And Ni you are given 1.5. Intrinsic carrier concentration is your Ni, which is given to use a 1.5 into 10 per 10 per centimeter cube. And KT by Q is given your 0.026. This is the same values you are given in the question number 10. And then you use the formula phi f
Oh,
equals to KT by Q ln Na by Ni.
okay, sir.
And if you solve this, the phi f you will get as 0.35 volts. Okay.
Okay, sir.
Yes, sir.
Sir,
Phi f you will get 0.35 volts. And in the question, you are asked 2 phi f,
0.70.
which will be 0.7, double of 0.35.
Sir,
Yes.
Yes.
whatever slide you are given, or we are see the slide 21 problem. Is this slide is only based on problems?
No, so not necessarily.
No, this slide is directly means your PPT will be same whichever you are uploading to the your means drive. This will be same PPT.
Yeah, it's the same PPT that I have uploaded.
Okay, okay, okay. Sir, if possible, sir, you can because you are uploading single slide. So if you upload this complete PPT, it will be sir beneficial for if we can directly solve this problem, sir. How many slides are there, sir? 63.
No, I have uploaded the whole PPT. One PPT for every week I have uploaded.
Yes, sir. I just told you that this is complete for week 7.
Yes,
Okay, okay, okay. Okay, sir. No issue. Okay.
the PPT I have shown in the like in the live session is the same PPT that I am uploading.
Okay, 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 okay. Sir, is there any PPT is there, sir, to all of the 12 session problems and assignment will be solved?
No, there is no PPT with assignment problems that.
Actually, sir, actually now it is time that in the exam, I think assignment will be whatever you told you and other when teaching assistant told that assignment will be very important for your exam purpose.
Yes, sir, because assignment is made by the professor, and he is also making the exam questions.
Okay, okay, okay.
So we don't have any relation with the professor, with Professor
Okay.
Divyajannath. What
Yes,
we are
yes.
showing is completely independent.
Okay, okay, okay. But sir, in a live session, teach means Digvijay sir told that question cannot be made by him. Question can be made by you, any one of you three guys, sir. I don't know what this is can be, sir. I don't know what who.
he
whatever.
he is the one. He is the one who will decide whatever question, whatever he's putting in the exam. I have no idea. We have never talked to Professor Nath.
Okay, okay, sir. Sir, if any problem is there for other student, otherwise, sir, you can discuss MOSFET little bit of little bit of sir, such that if we study, we can understand, sir. The
Yeah,
concept of
yeah. I will talk. I
if
will talk MOSFET in detail. So I was just going to complete this. So this is the answer for question 10, that it is zero point 0.7 micrometer, and then the same formulas, 0.7 zero point 0.7 volts, that you have to use in question number 11. So the formula for depletion width is given by this equation: under root of 2 epsilon psi pi s by q na. So,
Okay, sir.
and instead of pi s, you have to put 2 pi f, because you have asked, the question is asking you to calculate at the onset of inversion. And at the onset of inversion, the band bending you have just calculated 2 phi f, which is 0.7 volts. So you have to use 0.7 volts here. Instead of phi s, you have to write 2 phi f, which is 0.7 volts. And then epsilon si is given as your 11.9, and na is given as your 10 power 9, 10 power 16. So that will be your SQR 2 into 11.9 into 0.7 divided by 10 power 16. But see, this is 11.9. You have to also multiply epsilon naught here, which is 8.85 into 10 power minus 14, I think, for
the divide by term is there.
yeah, you have to also divide by your this thing. Yeah, so it's coming out your
3.30. 0.3 micrometer, sir. 0.3 micrometer. 8, 10 to minus 8 is there. Minus
so this
9 will
should
be
be
there.
10 power minus 12, and this is coming out as your point point 0.3 micrometer, which is your answer. So this 2,
Yes, sir. Yes.
this is your epsilon si, this is your 2 phi f, this is your q, and this is your na. And you calculate it, you get 3 minus 7, which is 0.3 micrometer. Okay.
Yes, sir. Yes, sir.
Yeah.
Yeah, this is probably last class or there will be extra classes there.
This is extra class only.
Okay, okay, okay.
So in this question, so you first have to calculate your COX. You have to use so so they should have given in the question the thickness of the
So it says Cox equal to epsilon ox by Tox.
yeah, but question does not give you epsilon ox. So if they're giving 11.9 for silicon, they should also give 3. 3.9 for silicon SiO2. So they should that should be there, and then you have to calculate the Debye capacitance. You have to calculate your depletion capacitance from depletion width, and using this formula, your depletion width that you just calculated. So the depletion width you have calculated as 0.3 micron. That you have to use here, and if you divide by 11.9, then use this formula 11.7 into 8 11. So it will be then
11.9 into sir.
8.854 into 10 power minus 12,
Yes.
1.05 into e power minus, that will be your epsilon SI, and then you have to divide it by point.
0.3.
Yes, so 0.3 if you divide it by
0.3 10 to the minus 9.
if you just divide it by 0.3, you will get 3.
Sir, you have to put the epsilon s also. 0.3 into 10 to the 9, sir.
10 to
Minus 9.
10 to
Minus
the power
9.
6, not 9.
Oh,
It's a
micro. Okay, okay. Sir, into होगा sir.
yeah. So this will be you what you get. You will get in
E boy.
in farad per centimeter square.
That per centimeter.
0.003, that is 3.5 into 1 2 3 4 minus 4, 3.5 into 10 to the minus 4 you will get. But this, I think you have to use Debye length here, which is different from your depletion width.
Yes, sir.
uh, I what I don't remember the formula for Debye length.
The Debye length formula is if I'm right. Its formula is sir lambda d equal to 1 by k. Root over of lambda d. Hello, sir.
Yes, yes.
Lambda d equal to root over of epsilon naught kt by n e square q square. N will be given sir intrinsic area concentration. Root over of
Okay, so I actually highly recommend you, if you want to learn more about this topic, MOSCAP and MOSFETs, and Like in general, you go through this chapters from Chen Ming Ho.
Can you share the link in the chat box?
This these all chapters are
For only sir MOSFET na entire course sir.
so it starts from your basic semiconductor. So electrons, holes. Then chapter 2 is your uh, recombination, motion. So you if you it will give you it goes it then this is your device fab microfabrication. Then this is PN junctions and Schottky junctions. Then this is MOS capacitor. Then transistor MOSFETs. Then this is scaling and short channel effects you will see here. And this is the bipolar transistor BJTs.
The dy is equal to root over of epsilon naught k kt by ab square q square sir.
P naught AQ or Q.
Yes sir, p naught means n square.
And KT by Q and then QN. Yeah, so this you can then you can just calculate as 0.026 divided by 1.6 into 10 power 16. This is coming out very huge value. I don't know why. I'm making some mistakes in the formula here, but and see, I will explain MOSFETs like now. See, this is how a MOSFET is. So you have a P region, and then source and drain are N plus. Then you have an oxide, and here the gate is also N plus. So, so if you draw, so if you take a cross section this way, like this, if you take a cross section, it will look like this. And where is it's oxide and then your semiconductor. And if you take a
Yes,
cross
sir.
section like this near the interface, then it will look like this. So this is your high, this is your N source region, this is your drain region, which are both N type, and the middle part your channel region is P type. So this is how it looks. And when you induce band bending here, this region goes down. It goes in the depletion or inversion region, and accordingly you can say that this band is coming down. So earlier you see there was a huge barrier here. So there was a huge barrier here. So there no current can go pass through this barrier. But now this
Yes,
barrier
sir.
is reduced. So now the current goes through. So now you have conduction between source and drain.
Yes, sir.
This is called gate induced barrier lowering. So you have heard double, right? So drain induced barrier lowering. This is gate induced barrier lowering, which is normal operation. Normally, we only want our gate to induce a barrier lowering. We don't want a drain to induce a barrier lowering.
Okay, sir.
And then this you remove the you put negative voltage or you remove the voltage. This again goes back to upside and becomes non-conducting.
Yes, sir.
So this is how it works. And you can see if you arrange an if you bring a voltage on your drain, so now your band looks like this. Your drain goes down because you have applied a
Positive
voltage
voltage.
on your drain. So your drain goes down, and now your complete barrier looks like this. So now you can have an electron flow from here to, from your source to your drain.
Yes, sir.
And you can see at the, if you take vertically, if I'm making a vertical cross section here, it looks like this. But if I am making a vertical cross section here near my drain, then it looks like this because of my drain induced lowering.
Sir, if I make a barrier at source,
Yes. So
the
if there's a barrier here, then your electrons won't be able to cross that barrier, so they won't be able to come here. So first your electrons have to cross this barrier here at the source, at this interface. Then only they can reach this interface and go to your drain.
okay, sir. First, you have to work on the barrier at the source. Then it can easily move to the drain.
Yes. Yes. So this source barrier at the source is what causes your conduction and non-conduction.
Yes, sir. I can understand.
So this is how your channel becomes. See, this is how your channel becomes, and as you increase your drain, your drain voltage. So this is when there is no drain voltage, your source and drain both are at, your VDS is 0. Both source and drain are at 0, but you have applied a gate. So you have formed a channel, but both are 0. So
Black channel is there.
there's a parallel channel, but as you give your VDS greater than 0, your channel your channel region becomes smaller near the drain.
Yes, sir. Yes, sir.
And if your VDS becomes equal, VDS becomes equal to your VGS minus VT, then your channel is 0 here. Your channel thickness becomes almost 0. That is called your pinch off region.
Pinch off. Yes.
And there then you have your saturation region there. So this is all your calculation that you do for this. If you want, so you use substrate charges to calculate, and by that you can get your drain current. So this is how your drain current look versus your VG looks like. So at above threshold it's looks, and below threshold it's a fast off. But so ideally this is 60 milli. This is sub threshold. This is called sub threshold region, and at sub threshold region your idle voltage, idle slope is 60 millivolts per decade, which means for every 60 millivolts your current increases or decreases by an order of magnitude. It gets multiplied or divided by 10.
Okay, sir.
So like at 60 millivolts, if your current is 1 nanoamperes, at 120 millivolts your current will be 10 nanoamperes. At 180 millivolts your current will be 100
100.
nanoamperes.
Yes, sir.
That is in the sub-threshold region. And the threshold region,
Saturation.
behaves like your linear and your square root region, because it's
Okay,
depend
sir.
current is VGS minus VT whole square, right?
Yes, yes, sir.
Yes. And so this is called transfer characteristics, where you plot drain current versus gate voltage, and this is called output characteristics, where you plot your drain current versus
VDS.
drain
VDS.
voltage. That is called output, and there's this then linear region, and then there's the saturation region.
Okay,
And
sir.
here you have below threshold, which is subthreshold, and above threshold, which is conduction region.
Okay, sir.
So this is just calculation of your drain current, different models. So there's a Pausa model for calculating your drain current. There's a Bruce model. Then there's a piecewise model.
Sir, these models are, I think, in, not in our syllabus, I think.
Yeah, that I am not teaching you all this.
No, no, sir, I don't. I know that. You just sharing the concepts.
Yes. So the values that the formulas that we use. So so you see, this is the formula that you use is called piecewise model
Yes, yes, sir.
because it divides divides your current into different regimes. So there's a below threshold regime, there's a which is called subthreshold regime, then there's a above threshold. There are also two regimes below pinch off in the linear and above pinch off saturation region. So use
Yes,
different formulas for all region.
yes, sir.
So you see, this is your formula for linear region. So this VGS minus 2 pi B is your VT. It's
BT.
basically what you write as VT. So you
Okay,
write
sir.
as VGS minus VT minus VDS by
BT is by
2
2.
VDS, right?
Yes, sir.
And
This is the linear region, sir.
yes, and then when VDS
Saturation.
becomes equal to VGS minus VT, this formula becomes same, and then you have your formula for saturation region.
In that case, sir, whole square is there in a term.
Yeah, because there's a this will become VGS minus VT. Then you have VGS minus VT minus VGS minus VT by 2. So that becomes your VGS minus VT by 2. And then this itself is VGS minus VT. So you multiply that, it becomes VGS minus VT whole square divided by 2.
Yes, sir.
So this is how it becomes in the saturation region.
Yes, sir. Yes.
And your M is basically a type of ideality factor. So you see here, it's your channel is pinched off.
Yes, sir. For silicon, it is 1, sir.
What? For M, your M value you are saying.
Yes, yes.
Yeah, so
For germanium, it is 2, sir. For silicon, it is 1 and germanium, it is 2.
so so this formula that you get is called your, and these are just different. So this now for subthreshold region, you calculate it with band. You can your formula, you took the base formula. You insert your 5s. You what all this rand. These are all different types of equations that you use to calculate, and ultimately you get this value, this formula for subthreshold, which is an approximation. But if you use this formula and then you calculate your subthreshold slope, it comes out to be 2.3 kT by Q 1 plus CD by Cox. And and if you write it in different terms, it it's dependent on E par Q VGS by KT.
Yes, sir.
So if we take log of this, it will be dependent on your VGS by KT. So that value is if you calculate for every 60 millivolts, your for every 60 millivolts, you will find that your current is reducing by current is reducing by your value of 10.
10.
Yes, so it's becoming 1 by 10 for every 60 millivolts. So
Okay, sir.
that is in the ideal case when your ideality factor is 1. That at that point it's at that point your subthreshold will be 60 millivolts per decade, but in more, so that's the thermodynamic limit for 300 Kelvin. The thermodynamic limit is 60 millivolts per decade. So mostly your subthreshold slope is larger than 60 millivolts per decade, like 80 millivolts per decade, 90 millivolts per decade. The best you can do is 60 millivolts per decade. And if you want to cross that limit, then the only option is to do tunneling current, because there the quantum factors emerge and they can help you cross the thermodynamic limit. By thermionic current or drift diffusion current, that cannot go below 60 millivolt per decade.
Yes, sir.
And then you have a body effect, where generally we keep the body at 0 volts, but if you increase change the voltage on a body, that will affect your voltage, that will affect your channel also, and that creates a body, that's called a body effect. It changes your threshold voltage. So you see, for body 0, it was, if your threshold was here, for body less than 0, your threshold shift to the right,
So,
higher.
sir, we require more amount of gate source voltage.
Yes, so you will have to give more you will have to give more gate voltage to get to your threshold if your body
Turn on,
if your
turn on
body
device.
voltage is less than 0.
Yes, sir.
So all this is given in great detail in this book by Tor and Ning. Like if you want to go every aspect of a MOSFET, if you want to study, you can go for this book, Tor and Ning. It's
Power and me.
it's very advanced, not recommended for this course, but if you want to study MOSFET in detail.
It is a total book PDF, sir.
What?
This whatever you show,
So
this is
this
the entire book PDF.
no, so these are lecture slides from the course that I studied here at IIT Bombay.
Okay, okay, okay. This can be only MOSFET or entire semiconductor.
So this was mostly MOSCAP and MOSFET.
Okay.
So the gate current formulas that we have studied till now, we had only we had we had considered that the channel is too large, too long. That so generally the formulas that we had studied, they had taken something called gradual channel approximation. We had there ignored the effect of the electric field in in lateral direction between drain and, so we are giving a voltage on the drain, right? We are giving a voltage on the drain, so that will also create an electric field between drain and source.
Yes.
But we assume that our channel is long enough that this this electric field, the change in electric field in lateral direction is very low, and we can ignore it. We can ignore its effects. So that is called our gradual channel approximation.
Okay, sir.
So, but when you come to short channels, that approximation is no longer valid.
Yes, because channel is short.
Yes, channel is short, so the effect of electric field is larger. So all these formulas that we had used, that mu effective and your length of the channel and your VT values, all these values will now become dependent on your drain current as well, your drain voltage as well.
Drain voltage.
Yes, and that is called your short channel effect. So, so you see these so in the middle region, your only the gate effect is there, but near their edges, near their source and drain, the charges are also see the effect of your source and drain. They are directly impacted by your source here and your drain here. So
Yes, sir.
so by short channel, so if, we have to then consider the effect of drain voltage on these these charges, and that causes our reduction in our gate length. And it, you see, it's so what happens is your it affects your, at a very high VDS, your VT also starts going down. VT also starts going to the left. So if you see, for the linear region, when your drain current was less, your VT was different, but at high drain current, your VT is more. Threshold is Your threshold voltage is increased for a high drain voltages. So it's shifted to the left now, and what that causes is at so, so if your threshold shifts to the left, so at VG0, your current is now higher.
Device will be turned on, sir.
Yes, so it won't be turned on, but your leakage current will increase.
Leakage current increase. Yes, sir. Yes.
Your off current at your current at VG0 is your leakage current, which is the current in your off state.
So it can affect the device performance.
Yes, increases. It basically increases your power
Off
consumption.
current. Off current.
Yeah, your off current is increasing. That means your leakage current is increasing. So ideally you want your leakage current to be zero, so that when my device is off, it is not giving out any current, so it is not consuming any power. It is not heating up. So if there's your joule heating is I square R, right?
I square R.
So if whatever current you have, the heating is double of that.
Yes.
It's proportional to I square. So
Yes, sir.
so it increases the heating effect also. If your current is higher, your heating will also be higher. So that will impact your device life also. If
Yes,
your
sir.
device is hot, its life reduces. Its performance is impacted. Uh, So what is happening is as you are increasing your drain, the the region where it's giving its a field effect is also increasing. And what happens is at certain point it it gets attacked. It merges with the
Upstate.
yeah, it merges with the region where your source current effect is there. So your charges here are seeing effect from both your source and drain. So now there's a apart from your channel, there's another path for your current to go from your source to your drain. So it causes a shortening of your threshold voltage. So channel becomes on quicker.
But sir, in off time, their leakage current will be high. In that case also.
Yeah, that is causing your leakage because the channel is now left shifted. So it won't have much time to reach your. So it can only go a maximum of 60 millivolts per decade, right? At in
Yes.
threshold. So if VT earlier was my, as I had shown during the lecture also here, if my VT earlier was, let's say, 540 and now it's earlier earlier my VT was 600 and now it's 540, then then so if I'm going down 60 millivolts, so I will have my leakage current increased by 10 because it will have 1 less point to decrease. If my VT shifts left by 60 millivolts, so 60 millivolts you would think it's not a huge value, right?
Yes.
60 milli. So VT is generally around 0.9 volts, 1 volt. What is 60 millivolts compared to 1 volt, right?
Nothing, sir.
Nothing. But that causes my leakage current to increase by 10 times.
Yes. So heating effect will be increased.
Yes. So my leakage current will increase, my heating effect will increase, my power consumption will increase. So we don't want my VT to get left shifted. So that is one thing. So there are preventive measures that they do. What they do is they create regions here. They create regions here which block charge, which block your source and drain effect to come to this region. There are these pockets where doping is very high. What they do is they reduce the effect of the source and drain to go through them.
Yes, sir.
Then next is your channel length modulation. So you see this pinch off region is there. So as you are increasing your drain higher than your saturation voltage, it's creating an increased effect of pinch off.
Yes, sir.
So that pinch off is increasing so your channel length is now decreasing because of that. So
Yes,
in
sir.
long channel effects, that this shortening of channel length was not that huge. Even in long channel, your channel length is shortening. This channel length modulation, that is there in long channel also, but 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 it's not considered, it's ignored because your channel length is considered much higher. But for short channels, this much this much channel modulation becomes a huge percentage. So like for long channel, if it was 1%, for short channel it becomes 10%.
10%. Yes, sir.
So 10% is a very huge value. So that
Yes,
what
sir.
that causes is, instead of saturation, you will have an increasing current because your channel length is shortening. So it becomes LCH minus delta LP. So
So IDSL value will increase, sir.
this value will keep decreasing. So your current
ID,
will keep increasing.
Yes, sir. It can also create sir heating effect in on time, sir.
What?
If the ID set value increase, it
Yes.
can also it can also create heating effect during on time
Yes.
because
Yeah, obviously your current is increasing, your heating will increase. So see, all you want, so this is, you are using it as a switch. You are using
yes,
you are using it as a, your MOSFET you are using as a logic gate, right? So you just need a 0 and a 1. You need a 0 state and a 1 state.
yes, sir.
So you don't want your current. So even at 0 state, you want your current to be low. At one, at on state, at off state also you want your current to be low. At on state also you want current to be low. But there should be enough separation between your off state and on state.
Exactly, sir. Exactly.
So let's say if my off state current is in femtoamperes and my on state current is in microamperes, that's a huge difference. That's a difference of 10.9.
Then
But
sir, power consumption will be very high.
power consumption will be very low. No, so on state is in microamperes, off state is in femtoamperes.
Okay, okay. Then your power consumption very low, sir.
But if my on state is in milliamperes and my off state is in picoamperes, my on off ratio is still the same. On off ratio is still 10.9. I can still do the 0 and 1. But my current in both on and off state is increased by 1000 times.
Yes, sir. So, sir, if your difference will be constant, that is not issue. If both value are increasing in due to effect, it can create some huge effect.
Yes, it increases our power consumption, it increases heating effects. So basically, I for switching I only need my I on by I off. On
Yes,
current
yes,
divided by off current. That should be sufficient enough so that my circuit can distinguish between off state and on state.
yes, sir.
So it can then assign 0 and 1 accordingly.
Yes, sir.
I do not I do not need high currents for that. I can do that in low currents also. And I prefer to do it in low currents because that will reduce my power consumption
Power
as well as
consumption.
my heating effects.
Exactly, sir. Exactly.
Yes. So any place where my current is increasing in both on state and off state is undesirable. So this is also undesirable. Next, we have got something impact
Impact.
ionization also, where the your field effect is very high here because of high drain, and that creates ions here, and
So, sir, device cannot be off, sir.
yes, that creates a huge energy here. That again we don't want that.
So, sir, in that case, if the short channel is there,
Yes,
so sir, without there is a off state will be very small time there because if I use short channel, the
yes,
direct leakage current will be direct go from source to drain without channel.
yes. So no, it there's a increase chance of increase of ton. What you are saying. So if my channel is in accumulation,
Hmm.
that is in accumulation region there is like you are not going that your saturation your tunneling current will still be chances of having tunneling current is still less because your channel is not that small. It's not in it's your tunneling current is in 1 to nanometers.
Okay, okay, okay.
So it's not that small that you have tunneling current. But what happens is even in weak inversion region you will have your so your even in weak inversion region you will have your current when your channel is not properly formed.
Yes, yes, sir. Yes, sir.
So that creates an issue. But more that is not that huge of a issue. But then your channel length modulation or your this thing your threshold voltage shifting.
These are more issues, sir,
Yeah,
compared
threshold
to
voltage shifting is mostly the point you're saying basically comes within threshold voltage shifting. So your channel is getting your conduction is starting in the weak inversion state itself. So you can say that your threshold shifts to your weak inversion region.
before channel forming current will be start flowing.
Yes, channel is still forming. It's not properly formed. It's not in strong inversion.
Okay, sir.
So it's near threshold. Your current starts flowing. So you can say that your VT is shifted to the left.
It also indicates that your leakage current will be high.
Yeah, because of that, your leakage current is getting higher.
Okay, sir. Okay, sir.
So then there's something called velocity saturation. So what it causes is the velocity, the electric field that is created, so the electric field is very high, so create your that will increase your velocity, and they will then saturate. Your velocity will become higher, and your then it will saturate, and what it will do is prevent your it will prevent your drain to create a pinch off region. So your before pinch off itself, your charges saturate, your current saturates. So current saturates before pinch off region. So that means that your VT gets shifted, and so all these are different. But because of your dibble, your even in saturation, your saturation point is coming before pinch off. But because of your dibble, you can still have an increase of. So dibble is drain induced barrier lowering, which is what we had seen here. This is dibble, where
Yes.
it induced the barrier lowering, which means it shifted VT to the left, and it constantly keeps shifting. So your barrier is because of that keeps increasing your current in saturation region itself, because the barrier keeps getting lower.
Yes, sir. Because it can increase your on current.
Yes, on current it can keep increasing, and so there are multiple reasons. See, your you are having your threshold voltage shifted. You are having your saturation current increasing. So both by multiple methods, your both on current and off current are getting increased,
Yes.
which uh, which are undesirable properties. So what more you want to know about MOSFETs?
No, sir. We can. solve some problem.
What type of problems?
No, no, sir. Means whatever you can share the concept, we can do this problem in my home. If anything is problem is there, I can contact through your mail, sir.
Yes, yes.
Sir, any kind of means
Yeah.
sir,
Say what you are saying.
sir, actually, sir, means sir, we have not studies are much harder, which is required for the maintain the actual conceptual. We are not doing regular studies, sir. That's why we are facing some problems, sir.
I think if you go through the lectures and write all the formulas and you go through the form, then you go through your assignments to try to solve each question. So now you have the answer also.
Yes, sir.
Assignment answers you also have. You go. The
That is it.
exam will mostly be what the professor has teaching in his lectures.
Yes, sir. And I think, sir, exam will be in multiple choice questions there.
I think it will be in multiple choice only. So
Uh,
I don't know if
Sir, you can get this. You can get this. Go to top, sir. Go to top. Exam format. Yes.
yeah. So here it's there. So if you go here, it will be. It's. I think it just says MCQ. Okay, it just says offline paper and pen or online. It's online, right? Computer based exam.
Yes, sir. So I think
It should be MCQ only. Then.
yes, yes, sir. Yes, sir. Sir, so uh, what is, sir? You can do any NPTEL courses, sir, in your.
I haven't done any NPTEL course.
I know that, sir, because you have your own your coursework.
Yes. So like no, but like NPTEL are good courses. You should, but I have not done any NPTEL course.
No, sir, actually, I just want to get some experience from you. If you give any NPTEL course exam, you have got a little bit idea that how, because sir, we are working candidates.
Yeah, I understand, but I have not done any NPTEL course till now.
This one, sir, this one. 275, sir, 275. Our course is 275.
No, this is 290. This one, right?
No, no, no.
It's this one,
Oh, yes.
290.
290, 290, yeah. 290, sir, 290. Yes, yes.
It just says online computer based. So it should mostly be MCQ only.
So, sir, means, okay, sir. First of all, sir, you can close the recording because,
What?
sir, if possible, you can stop recording, sir.
Any issues?
No, 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 sir. Actually, I just want to say that. So, as per your means opinion, whatever assignment, whatever concepts sir will discuss, that is enough for the exam purpose.
I think they should be enough. So if you do go through the assignments, any extra concepts that he wanted to you to know will be you. If we are solving the assignment question, you will learn those extra concepts from the internet, right?
Okay, 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 sir. If we are facing some problems, sir, we can mail you. You can reply on the mail, okay?
Yes,
If
yes.
possible, sir.
If you mail me and I am able to answer, I will answer.
Okay, sir. Okay. Thank you, sir.
Thank you.
Good night, sir.
Good night.